Firstly, I would like to express my gratitude to the organizers for giving me an opportunity to present these lectures. It's really gratifying to see that, Lattice activities are being, you know, taken seriously in this institute, because in '86 when I joined, there were many of us working not so much in simulations as in the foundational aspects which I'm going to talk to you about. Now, what I'm going to present is not going to be any detailed derivations or equations. This is more an enumeration and some explanation of what I think are the essentials of the foundations of lattice field theories in general. And lattice gauge theories, of course, will be a part of that. There will be things that I'll be presenting here which may not be available easily in standard, books on lattice gauge theories and so on. And I don't expect you to understand everything. Just recall, and you can always go back to it later on, or comment, discuss with me anytime, during this entire school. If necessary, maybe we can even have a few informal sessions where I can explain some of these things in greater detail. So first let me start with some references. This is a very, very small, personalized list of references. Clearly there are lots of books, review articles and so on lattice gauge theories, but for the purposes of my presentation, these will be the ones I would suggest. All my talks will be essentially taken from my book written about the effective string theory of QCD strings. It was all work that was done here with the supercomputer that I had built and into various analytical directions. Chapter 20 of the book is entirely devoted to what I call essentials of lattice gauge theory, and this is going to be more or less a recounting of that chapter. However, in that chapter, I did not touch on fermions at all because the focus was on Yang-Mills flux tubes of pure Yang-Mills theory. So for that, here is an article which I wrote some time ago about regularization of chiral gauge theories, of which standard model is one. And there are parts of that article which focus on how to introduce fermions on the lattice. Hopefully I'll get to that, and I'll even try to explain why putting the standard model on the lattice continues to be a big challenge. And here is something which I wrote almost 40 years ago when I was in NICEF Amsterdam, because many experimentalists wanted to understand what's all this lattice gauge theory about, and I explained in detail the essence of lattice gauge theory again. And this you can download if you go to HEP Spice and look under my name. A PDF is available and you can download that, and that should also help you in understanding quite a bit of my lectures. And then there is this wonderful monograph written by my friend Erhard Zeiler on deeper reasons for why lattice field theories are important. Okay? I don't know whether that is available in the library or not. I have my personal copy and you're welcome to use it provided you give it back to me by 5 o'clock every day so that if I need to prepare, I can still have that. My book is available in the library, and maybe you can negotiate with the librarian on some creative way of using that book. I don't exactly want to spell out the nitty-gritty because that may amount to encouraging copyright violations, but I'm not a serious believer of intellectual property right when it comes to textbooks. Okay? So that is 4 references, and that I believe should suffice. These days, whenever I want to talk on any topic, be it quantum mechanics or gravitational waves, I like to ask 2 questions. One, why? The other one is what? So why quantum mechanics? And then what is quantum mechanics? So why should we bother about lattice field theories? And then other question is, what are lattice field theories? Both are important questions. So there are 2 sides to this question of why lattice field theories are important. One is what I would call a utilitarian side. Okay? And that utilitarian side mainly consists of how, combined with more and more powerful computers and more ingenious algorithms, lattice field theories, lattice gauge theories, lattice spin field theories have dramatically improved our understanding of these subjects, because analytically these are all extremely difficult questions to analyze non-perturbatively even to this day. I sometimes worry whether all this numerical support from lattice field theories has somehow inhibited people from thinking deeper about analytically addressing these issues. So it will be good if some of you guys can take up, thinking deeply to see how much of what we have learned through simulations can really be understood analytically. So that's a utilitarian side. And for example, if you take QCD, there's a question of confinement, there's a question of what are monopoles in QCD, and topology of gauge fields, spectrum, of which you're going to hear, I'm sure, in this school, non-perturbative Higgs phenomena, etc., etc. Every year we have lattice field theory conferences, hundreds of papers are presented, and that is a testimony to how far the lattice field theories have come. In 84 was the first lattice field theory that was held, and I used to live in Holland at that time, and just a handful of us thought that we should start some regular meetings on this topic. And today that has grown so much, both in scope as well as in the size of the lattice field. Now, incorporation of fermions into the lattice field theory scheme is very challenging, and I will try to touch on that, but it is rapidly approaching very respectable levels. And the testimony to that is the increasing accuracy and precision of lattice results, including fermions. Even in the precision front, the lattice theories have come a long way. Very recently, there was a lot of excitement about the muon G-2. And the precision of lattice calculations have reached a stage where the actual high precision measurements of G-2 can be confronted with lattice calculations. In Sven Wolof's talk this morning, we saw that the precision on the fine structure constant is the best from the lattice simulation. But you have to be very careful in honestly judging the error bars, because the systematic errors in lattice theories, assessing them can be quite a daunting task. But experts assure you that they understand these things quite well. There are still some outstanding field theories which we have not succeeded in bringing to the fold of lattice theories to our satisfaction. And one is supersymmetric field theories, both gauge and non-gauge. And that, you may say, is not such a alarming situation, because we still don't know whether supersymmetry really plays any role in nature's schemes. But nevertheless, it's a very interesting challenge to realize supersymmetry on the lattice. And the difficulties of putting supersymmetric field theories on the lattice have prompted people like my friend Holger Nielsen to think that they probably don't even exist. Okay? But now that may be an extreme viewpoint, but it's a very, very interesting area in lattice field theories, namely understanding how to put supersymmetric field theories on the lattice. Another much more important to us particle physicists is the difficulties in putting the standard model itself on the lattice. The standard model is an example of what we would call a chiral gauge theory. Okay? It's a gauge theory of chiral fermions. And in fact, the difficulties both in putting the supersymmetric field theories on the lattice and putting the standard model on the lattice are intimately tied, and they have to do with both the technical as well as conceptual difficulties in describing chiral fermions on the lattice. That reference that I gave you discusses this in great detail. I don't know whether I'll have the time to discuss chiral gauge theories. At least I'll try to explain what the problem is in putting fermions on the lattice. Okay? That is the utilitarian side. But there's a deep conceptual side as to why lattice investigations are very, very important. This is because the quantum field theories, as taught and propagated and practiced, are ill-defined. Mathematicians wouldn't even touch them because the very opening line makes no sense to them. Quantities are all singular, they diverge, and they don't exist in the sense a mathematician would like to see. And that's a serious problem because you have a theory that's not even well defined. So you have to be very, very careful about it. And these divergences come if you do the operator approach, because the product of quantum fields at a point are highly singular. Or if you do the path integral approach, the measure is very complicated and singular unless you very carefully regulate it. Now, in perturbation theory, this manifests as divergences of the loop integrals. But that's a perturbative approach, where you're looking process by process, write down the Feynman diagrams, and try to evaluate the loops and so on. But you might want to take a broader look at the entire theory itself. So you tame these divergences of the loop integrals through regularization and renormalization. But if I want to give meaning to the entire theory, then I don't want to break it into processes, look at it diagram by diagram. Okay? So we want to give quantum field theories a mathematically well-defined meaning for the entire theory. And this is what is often called a constructive approach to quantum field theory. You construct the field theory, so when you construct at every stage, everything is concrete. It's like the way a building is built. You, brick by brick, construct it. And at every stage, there is no question about the bricks being meaningful or being real and all that. Okay? Now, that is where the real impact of lattice field theories comes. And lattice approach, as of today, is the only known way of defining quantum field theories constructive. There is no other way. Okay? So that is what I would call the conceptual answer to the question, why lattice field theory? Erhard Zeiler's monograph that I quoted in the references does a very beautiful, systematic job. In fact, the title itself is, giving field theories a constructive meaning. He doesn't unfortunately put lattice in the title, but the whole monograph is about lattice construction and defining field theories non-perturbatively. So that is the second coin to that question. Now I will go into what I call the three pillars of the lattice formulation. They are the real essence of the lattice formulation. And I will enumerate them one by one. And the first is the path integral. Excuse my spellings. I do know how to spell integral. It's just that yesterday, after a very tiring journey from Mysore, I started writing this. So there will be a lot of typos and grammatically incomplete or incoherent sentences. So the first of the pillars is the path integral quantization of field theories. So in quantum mechanics, this is the beautiful formulation of Feynman in 1948, that the probability amplitude for a particle to be found at position xf at a later time tf, given that it was definitely at xi at time ti. This is sometimes called the kernel of the path integral, but you don't need path integrals to make sense of it. It's just the probability amplitude which can be calculated even with the help of Schrodinger equations and so on. But what Feynman did was to give a representation for this quantity as a sum over all possible paths that connect the initial and the final points with a certain weight factor, which rather surprisingly is the classical action for that path divided by h bar. Now we've all been told that there are no trajectories in quantum mechanics. Then why are we talking about trajectories here? What is not there in quantum mechanics is a trajectory in the sense of a solution to the equations of motion which gives a position as a function of time for all times. Because in order to do that, you need to know both the position and the momentum with arbitrary accuracy, and that quantum mechanics doesn't allow. But it certainly allows a sequence of measurements where at one time you get one position as an outcome, at another time you get another position as an outcome. So it's a quantum trajectory. It certainly is not the solution of any equations of motion of the theory. In that sense, of course, there are quantum trajectories and they are infinitely many, because at each instant the outcome of measurement is completely random. Okay, so you have actually infinitely many of these trajectories, and the amazing thing is that if you weigh them all with the classical action, then you get the quantum mechanical amplitude. It's very ingenious, but it's not new quantum mechanics. It's just a new representation for what was already known in quantum theory. Okay? But sometimes finding different representations for objects that you already know is very useful, because with the new representation you can do more things, make more mental images, and in fact that's the role the path integral approach to quantization has played. There is a mystery here in a way. Of course, that mystery is superficial, and that is, how can purely classical action determine the entire quantum mechanical property of the system? Okay? Now, this is a deep question which should be understood, and the answer depends on the measure. Okay? Now, when it comes to path integrals, there is a folklore of how Feynman met Herbert Yale in a bar and they started talking about it. By the way, I met Herbert Yale in Max Planck Institute, and he's supposed to have told him, look, Dirac has written this. Now, if you look at Dirac's quantum mechanics, there are 4 editions of that. If your library is really a good library, it will have all 4 editions. And I welcome you to look at every edition and see how Dirac himself changed his mind on this part from one edition to another. So if you only see the 4th edition, you miss out a lot about how Dirac actually thought about this problem. So the folklore is that Dirac had some preliminary ideas which showed how Lagrangian, actually more precisely actions, are important in quantum mechanics, and Feynman built on that. This is not entirely true because it turns out that Dirac had the full path integral formulas. You have to read, as I said, from one edition to another. Not only did he have the full path integral formulation, he had a formulation which was much more general than what Feynman gave. If you're interested in this, you can see this article I wrote, few years back in 2020 on Dirac and the path integral. So let's go into this Feynman path integrals a little deeper. Now the Feynman's method, if you for example look at his book written with Feynman and Hibbs, it's a beautiful introduction to the subject. He actually shows you how the path integral comes out from the standard formulation of quantum mechanics. Okay, it's just introducing a whole lot of completeness relationships and working it out, and then the path integral formulation just falls out. And it is quite illuminating even to understand the free particle case or the harmonic oscillator. Now, the reason why Feynman's method worked was that he always had Hamiltonians that are quadratic in moment. Now, there are many Hamiltonians which are not quadratic in momentum. The Dirac Hamiltonian is actually linear in momentum, and for those cases, Feynman's method doesn't work. You have to actually do some extra work. But the generalization to quantum field theories more or less goes through, at least for bosonic field theories. But when you come to fermionic field theories, again, it is not so straightforward for the same reason that the Hamiltonian for the Dirac case depends linearly on momentum even in the field theory case. Now we can extend it to gauge theories, both abelian and non-abelian, and I will do some of it explicitly. Now when it comes to fermions, there are all kinds of subtleties. It turns out that if you look at the fermionic field as a coordinate, its canonical momentum is psi bar. Okay, so there is some kind of a constraint relating both momentum and coordinates, and this makes the fermionic field case actually more like a gauge theory case, and you have to be very, very careful about it. So you actually need an integral that involves functional integral both over psi and psi bar. The other problem is fermions are obey Fermi statistics, and the only way to realize this is to interpret these field variables as Grassmann numbers. Grassmann numbers are anti-commuting, okay? So if you square the same variable, you get 0. Now Grassmann numbers are not like ordinary numbers, so in numerical simulations, with fermions, you can't use your usual way of computing with real numbers. And that's a very, very big problem. However, if you have only one Grassmann number in the world, you can represent it by a 2 by 2 matrix. That's wonderful. But if you have two Grassmann numbers, you need the matrix which is 4 by 4, and if you have n of them, you need matrices which has 2 to the n by 2 to the n. So if you take even a reasonable size lattice with fermions, with various colors, spin, degrees of freedom. These matrices are so huge that it is hopeless to work with them. Now, you can, of course, most of our physics theories involve the fermions as quadratics. So you can integrate them out and don't ever see them. But the problem is they leave behind determinants of matrices which are as big as those, and the problem comes back in another way. Now in quantum mechanics, that path integral had the meaning of the amplitude to go from one position at one time to another position at another time. Okay? So what is the meaning of the field theory path integral? And the field theory path integral has the meaning of the probability amplitude for the vacuum of the quantum field theory at very distant past to go into vacuum of the field theory in the distant future. If there is nothing happening, this amplitude should be 1. But in any case, it's a number, so cannot have too much information about field theory. But formally, the path integrals of field theory are like partition functions of statistical mechanics. But the partition function in statistical mechanics depends on temperature, and it has a lot of information. If you are able to calculate the partition function of an equilibrium statistical mechanical problem, you can get the free energy from that, all of thermodynamics. But the quantum field theory partition function has no parametric dependence. So it looks like it is useless, and it indeed is useless. What is more useful is quantities like this, where, sorry, this is a typo again, where you evaluate the path integral, functional integral with this added factor, and this is the vacuum to vacuum amplitude in the presence of external sources, and a lot of things can happen, and that need not be 1. Depending on what sources you put, this amplitude has a lot of information, and formally, by taking the derivative of this and evaluating it at j equal to 0, you get correlation functions of this type, and you can generate all the correlation functions of the field theory with the help of z of j. And this entire family of correlation functions contain all the information about quantum field theory. They codify the entire quantum field theory. Okay? This is the exact analog of what is called the Whiteman function in axiomatic field theory. In axiomatic field theory, Whiteman said, if you know all the correlation functions of this type, you know everything. To see how it works, you can, for example, look at the non-perturbative calculation of a scattering of 2 particles into 2 particles. Not perturbation theory. You don't write down Feynman rules, and you don't do loop by loop. This is the entire answer, and the formalism to do that is called the LSZ formalism. Lehmann, Simanzik, and Zimmermann. I happened to meet both Lehmann and Zimmermann. Unfortunately, I never got to meet semantic. In my book, there's an entire chapter devoted to the LSB formalism, and there you can see how knowing time-ordered correlation functions like this, you can determine non-perturbatively the entire scattering amplitude. This LSB formalism in the early days was quite heavy, and when we were students, we used to joke about it, calling it the LSD formalism, because it's quite a heavy trip to actually understand this. But it's not that difficult. It's actually very beautiful, very systematic, far prettier than perturbative calculations. Okay? So this is about the importance of the so-called Whiteman functions. Now again, coming back to path integrals, in quantum mechanics, if the Hamiltonian has quadratic dependence on momenta, you can integrate out the momenta as Feynman originally did and write the path integral entirely in terms of position variables, and those are called configuration space path integrals. But if you cannot do it, you will need functional integration both over position and momenta, and these are called phase space path integrals. Both types are heavily used in statistical mechanics. So the Dirac fermionic field partition functions are of the configuration type, phase space type of path integrals, whereas scalar fields, gauge fields, etc., they are of the configuration space type. Now, as I said, if the fermion fields appear as bilinears, you can integrate them out. But even if they are not bilinears, suppose it is psi bar psi to the fourth power, then you can introduce an auxiliary scalar field and rewrite this quartic interaction as action involving the auxiliary scalar field and only bilinear fermionic fields, and you can again integrate out the fermions. Now, path integrals were formulated by Feynman in 1948. That is the first pillar. You may wonder, how can any structure be stable with three pillars? Okay, it requires some ingenuity. Try building a chair with only three legs. You can do it, but you have to be quite a skilled carpenter. And in fact, if you are not a skilled carpenter, even four legs actually don't help. As anybody that has tried to fiddle around with carpenter. Now I come to the second pillar for path integral formulation, and this is Euclideanization. This is a truly mysterious aspect of quantum field theories. We still don't understand why it works. Okay? Now, when you do Feynman rules and compute loop integrals, often one Euclideanizes that momentum integral, but that is just for mathematical convenience. You may do it or you may not do it. So that is not the true power of Euclideanization. What we are going to discuss now is Euclideanization, not process by process, but of the entire theory. Okay? Is it possible? Does it make sense? So this is formulating theories in a world with Euclidean metric instead of the real Minkowski metric. Now we all know that there is a dramatic difference between Euclidean space-time and Minkowski space-time. In Euclidean space-time, there is no time, no causality. But in real world, both time and causality are indispensable. They are the very stuff out of which our descriptions are made of. So does it really make sense to Euclideanize? Why would you even bother to do it? Is a question that you can ask. Now, of late, science journalism is it has gone completely out of control. And if you do a Google search, even if you don't do Google search, if you do Google search on Chole Bhature, you will still get something about time, wormholes, and all that. And there is a lot of hype about how there is no time. You have to approach all these things very cautiously. Long ago, there was a joke. There used to be a young boy called Guru Maharaj Ji, and once when he was returning from his foreign trip, the customs guys found his suitcase was full of watches. And it looks apparently that this guru told all his devotees, there is no time, so just throw away all your wristwatches. But there were two buckets. In one you put watches like Rolex and so on, and in the other you put HMT watches and things like that. And so he collected all these wristwatches, telling his devotees there is no time. So Euclidean world, there is really no time. So what relevance is it to physics at all? To get some idea about why anybody would even want to think about Euclideanization, let's look at the propagator, free propagator in Minkowski space, and that is of this form. It is singular on the real axis, and we make it complex by the I epsilon prescription, and depending on your boundary conditions, whether you want retarded Green's functions or advanced Green's functions, you choose one sign or the other. There are actually two complex propagators, and they are, of course, related in a way, but they are independent Green's functions. In contrast, if I Euclideanize it by making P naught to IP4, then this becomes of this form, no singularities, and it's a single function, real function. So in the Minkowski world, we have two Green's functions, reflecting the fact that causality has two types of solutions, retarded and advanced, and in Euclidean space there is no time, so there cannot be any distinction. So there is only one real function. But nevertheless, this one real function knows about the two complex functions in the Minkowski space. So there is some way of continuing the Euclidean answer to Minkowski space-time, which gives the correct Minkowski Green's functions. If you think about it, this is actually quite miraculous. There is no reason why the Euclidean Green's function should have known anything about the Minkowski world at all. Now, one point which you must emphasize is that Euclideanization is an independent structure on its own. It has nothing to do with lattice, nothing to do with path integrals, and in fact, Euclidean field theories were discussed long ago in the continuum field theory. Okay? That's very important to keep in mind. Therefore, on these three pillars, the pillar of path integrals and the pillar of Euclideanization, They stand on their own right. They are independent structures. Now let's get deeper into this idea. Schwinger, the great master of quantum field theory, he introduced this idea of Euclideanization in 1958, 10 years after Feynman had formulated his path integral formulation. And it looks like a bolt from the blue because why Schwinger ever thought of this is not very clear. And Schwinger in his writings doesn't give any clue as to why he did things the way he did. He just presents it. And in fact, even listening to Schwinger giving lectures, I sat through his lecture on quantum mechanics in UCLA. He doesn't allow any questions to be asked. And it is a magician's performance where rabbit after rabbit comes out of his hat. And then you say, yeah, that's wonderful. Now I understand how these things work. And in the evening you try to reproduce and you can't go beyond the first line because, it's like a magician. You don't really know how things are done. So that is Schwinger's approach to physics. Some people don't like it. They contrast him with Feynman and they say, yeah, but Feynman made things understandable so much better than Schwinger. I don't agree with him. I'm a great fan of Schwinger. With Schwinger, you have to keep on reading. Now, I have been reading his theory of quantized fields for the last 40 years. Okay? And each time I learn something new about quantum fields. That's Schwinger for you. So he introduced what he called the Euclidean postulate in 1958. And a year later, the Japanese physicist Nakano also came up with the same idea, though Nakano's elaboration is not as magical as Schwinger's, but it is the same. So we should give both Nakano and Schwinger the credit for coming up with Euclidean postulate. So what is this Euclidean postulate? Let's use Schwinger's own language. He said the amplitudes of a relativistic quantum field theory continue to be meaningful under the mapping of Minkowski space onto Euclidean space. Meaningful in what sense? We'll come to that. Meaningful in the sense a detailed correspondence can be established between relativistic quantum field theory in Minkowski space and a mathematical image based on a Euclidean manifold. That mathematical image he calls it because that has no time, no causality, okay? So it's only an image, but this is one where the image has all the information about the object. So he also said it in a rather expressive, almost poetic manner, and he said it's as if nature formulated her thoughts. Now don't attack me for saying her for nature. If you prefer, you can call him for nature or it, whatever. That's not important. Whoever, if nature is a person at all, that it's as if nature formulated the thoughts first in the Euclidean language and then rendered them into the Minkowskian world. Okay? So the primacy, according to Schwinger, is in the Euclidean formulation. And the continuation of that is the Minkowski field theory that we all study and love and apply, and hopefully we'll get jobs because of how well we have applied this. That is rather striking. Okay? But that is poetry, and you have to be a bit careful with poetry because while it sounds very nice, it's also very vague and ambiguous, and depending on interpretation, you can interpret a poetry this way or that way, and it sometimes in completely orthogonal ways. We physicists want something more reliable than poetry, and we want it in mathematical terms. So we want to express this correspondence in mathematically precise manner, and the Euclidean postulate says that there is an exact correspondence between the Weightman functions, which I already introduced for Minkowskian field theories, and the vacuum expectation values of the time-ordered products. They are supposed to have all the information about quantum field theory, and Schwinger functions. And Schwinger function is vacuum expectation value of a chain of Euclidean fields. What vacuum here means is a little subtle, and let's not get bogged down on that. Now, in trying to motivate this Euclidean postulate, Schwinger gave a lot of, perspectives in support of why such a postulate can actually be correct. Mathematicians had already known that some representations of the Lorentz group, only some, could be obtained from the corresponding Euclidean group, because for mathematicians, the Euclidean group is well defined. There is a group of transformations that leaves a Euclidean metric invariant, and likewise the Poincare group, or the smaller part of it, which is the Lorentz group, and you can look at the representations. Okay? Perfectly well-defined mathematical activity, and very beautiful stuff. So what mathematicians knew was that some representations of the Lorentz group, you can obtain it from some representations of the Euclidean group through what is called a Weil unitary trick. Okay. But what Schwinger now says is the Euclidean postulate goes further, and it says that all representations of physical interest of the Lorentz group can be obtained from suitable representations of the Euclidean group. Okay? So that's the full mathematical content of the Euclidean postulate. Now, what we said about propagators now can be generalized to all Green's functions, and the statement is that all Green's functions of the Minkowski theory are complex pairs coded by a single real Euclidean Green's function. So that is the Euclidean postulate in put another way. Now this was 58, 59, and not many people took notice of it because they didn't see, maybe the usefulness of this concept. And it took 15 years till Osterwalder and Schrader came up with a very powerful paper called Axioms for Euclidean Green's functions. This came out in 1973. They formulated the exact conditions the Schwinger functions must satisfy so that they can be mapped into suitable Minkowski space Green's functions. Precise conditions. Very powerful result, but simple. So they introduced a notion called reflection positivity. Now, Unfortunately, I'm not able to explain this fully. It's involved, but no sophisticated mathematics is needed other than the fact that squares of real numbers are always positive or zero. That's essentially all the mathematics you need, but the proof is, kind of a tour de force, and Zeiler's monograph goes through this very carefully. And the challenge was to find these for gauge theories, for fermionic field theories, etc., etc. So the answer now is, if your Euclidean Green's functions satisfy reflection positivity, then you are guaranteed that there is a unique continuation from Euclidean space to Minkowski space. Therefore, it becomes useful to study Euclidean Green's functions because there is the simplicity of only one function for every pair of complex Green's functions in the Minkowski's case, and many others. Now, this reflection positivity is so powerful that it not only guarantees a continuation from the Euclidean space Green's functions to Minkowski space Green's functions.
No, I was just asking this emphasis on Euclidean theory first and then.
I forgot to tell you, I have a problem with hearing, so I probably won't hear what you're saying. So maybe if you can just scribble it on a small piece of paper, I'll be happy to answer you. Or somebody must relay it to me.
I can speak really.
Speaking through the mic. Speaking through the mic.
Should I go ahead?
Yeah.
Okay. So this emphasis on Euclidean first and finding all the Lorentzian results from there through continuation, does this philosophically go through for curved space?
Can you repeat his question?
He's asking what happens in curved space for this reflection positivity arguments.
Yeah, curved space generalization.
I'm sorry, this is old age.
He's asking about what happens to reflection positivity arguments in curved space time.
Yeah. Good point. I'm only talking about relativistic quantum field theories on flat space-time. There is no formal proof of the type of Osterwalder and Schroeder for non-trivial space-times. And even if the topology is reasonably simple, just the curvature of space-time, doesn't allow many of these proofs to go through. So for general space-times, we don't have the analog of Osterwalder Schroeder, at least as far as I understand. Maybe Ramesh, knows better if there has been any improvement on this question.
There are some metrics proof will go through, but not all metrics. That's probably the best way.
Okay. Now coming back to the power of reflection positivity, flat space-time. So as far as our quantum field theory is relevant for particle physics, this all goes through, and for the purpose of this school, maybe that's all you should care about, okay? But if you're going to ask me what happens in the vicinity of a black hole, I have no idea. Or in cosmology. Now the reflection positivity guarantees something even deeper. And you see, our Minkowski field theories, they're equipped with a positive norm Hilbert space and unit array. Without that, the theory makes no sense. Probabilities cannot become negative. Okay? So this is an essential property of Minkowski space field theories that must be guaranteed to emerge from the Euclidean Green's functions And rather amazingly, reflection positivity is enough to guarantee that, and it invokes what are called transfer matrices. And in statistical mechanics, these transfer matrices have played a very powerful role in delivering a lot of results. For example, when much of the pioneering works of Baxter in solving exactly solvable statistical mechanical problems involves transfer matrices. And later, I will try to construct a simple but sufficiently illuminating example of a transfer matrix and do the calculations explicitly. Now, that is extremely important. Again, Silas' monograph explains beautifully how all these results come from reflection positivity. Now, fermions, you don't have to go to non-trivial spacetimes, even in flat spacetime, fermions cause some problems for Euclideanization, but they can be overcome. The reason is fermions are based on Clifford algebras, gamma nu plus gamma nu, 2G. Now, Clifford algebras are sensitive both to dimension, that's why fermions in odd dimensions and fermions in even dimensions, they work very differently. And they're also very sensitive to the metric. In Euclidean space, you can choose all gamma matrices to be Hermitian, but in Minkowski space, that's not true. If you choose gamma naught to be Hermitian, all the spatial gammas become anti-Hermitian and vice versa. That's just a simple illustration of how metric has a profound effect on the description of fermions. Now, here comes what can be called a boon from Euclideanization. This alone is enough to justify looking at the Euclidean postulate very seriously, and that is the QFT integrals, apart from the measure which is very, very formal, also have an oscillatory integrand, e to the I s classical, and these integrals are infinite dimensional. Just imagine integrating an oscillatory function even in 1 or 2 dimensions, you will realize the path integral is hopeless because that integrand is oscillatory, and here is what Euclideanization does this. It cues this problem in a dramatic way, laying the very foundations of lattice theories. What is that? So let us illustrate it with just a scalar field theories. So this is the Euclideanization of the time coordinate. It takes a Minkowski metric into the Euclidean metric. The 4-dimensional Minkowski element goes from d3x dt to I dxi. In fact, in the last lecture, somebody asked why there is an I in the action. There shouldn't be. If it's a Minkowski action, there should be no I in that. Okay? Maybe the speaker had the Euclidean action in mind. I don't know. Now, if you take a Lagrangian for scalar field theory, it's an element. Now, V of y has to be positive definite, otherwise the Hamiltonian will not be bounded from below. And you can Euclideanize it very easily, and this becomes minus sum of squares plus V of y, which is already positive semi-definite. So the Euclidean Lagrangian density is less than or equal to 0, which means I times S classical, if you keep track of how t goes, becomes minus S Euclidean, where S Euclidean is greater or equal to 0. So this oscillatory integrand becomes a perfectly convergent integral for the path integral. And that's why lattice gauge theories work in practice, and this is an amazing boon to lattice gauge theories. In gauge theories also same thing happens, provided you take care that all the temporal components of the gauge field are transformed the same way as you transform time. Okay, minus I, that's very important. So you can Euclidenize scalar field theories, gauge theories, fermionic field theories also with some care. But there's a big exception, very interesting exception. If you look at the Einstein-Hilbert action for gravity and Euclidenize it, you get a Euclidean action which involves the scalar curvature for Euclidean manifolds, and that is not of a definite sign. Scalar curvature can be both positive and negative. If you take two-dimensional manifolds, this is flat in this section, and that is positive curvature, this is negative curvature. Therefore, it's no longer true that the Euclidean action provides a damping factor. So gravity is exceptional, and this is potentially a thorn in the flesh for quantizing gravity through path integrals, something which Hawking has been selling for a very, very long time. So I stop here. I hope I've given you an idea of the first two pillars, namely the path integrals and Euclideanization. The third pillar is discretization, and you put all these three together and you get lattice gauge theories, and we will see how it goes. And after it has been set up, I will try to work out an explicit example of how transform matrices work, and the very important property that positive transform matrix is what you have to have for the Euclidean theories. Thank you. Are there any questions? Please feel free to ask. And Padmanath will have to ask us the relay.
Am I audible? Can you hear me? Yeah.
Yeah.
Probably going to need the mic.
Anyway, you can come closer.
Yeah.
So my first question was, okay, I have written this this axiom of QFT for temperature not equal to zero or non-equilibrium field theories. Does that hold? This Whiteman.
Well, at the moment I've only talked about zero temperature field theories. I am very conservative in this matter because I think there is no separate finite temperature field theory. If you know the Hamiltonian of the zero temperature field theory and its spectrum, the finite temperature partition function can be calculated unambiguously. So when sometimes confusions are generated for finite temperature field theories, I think this is some carelessness in doing that.
Your answer will hold for even non-equilibrium field theories. For even non-equilibrium field theories.
Non-equilibrium, I have no idea. Only thing I know is that we are all non-equilibrium, otherwise we would be dead, right? But otherwise, I don't understand non-equilibrium statistical mechanics, because unless you put some restrictions, non-equilibrium can be anything from ballistic motion, to various organized motions, etc. So we cannot have the same simplicity as equilibrium statistical mechanics. So when people talk about non-equilibrium, it's a very important problem. Okay, everything in life is non-equilibrium, but general principles about non-equilibrium
Yeah. So,
stat-mech I don't understand.
yeah. So basically, I can take this as a take-home message that everything cannot be reduced to this Weightman function, vacuum Weightman functions for like in general, not like non-equilibrium, right? But you say that at finite temperature equilibrium, you can assume that everything.
So what I would say is solve the zero temperature field theory first. Okay. Get all the spectrum, energy eigenvalues, degeneracies, and so on. Then you know what the partition function of the finite temperature thermal field theory is.
Right. Yeah.
In practice, you may not be able to do that. Okay.